before that the types of reactions, like double replacement, single replacement, those kind, we need to know those in Chem AP, but that's not what we're focusing on for our types of reactions in this unit and this year. The types of reactions that we are going to focus on include precipitation reactions, acid-base reactions, and oxidation reduction reactions, also known as redox. We briefly touched acid-base reactions with our titrations last unit, or last section, and we will go into more detail in a bit later on. And redox reactions, we actually covered those a little bit when we went to that Purdue lab about electrochemistry. We learned about oxidation reduction, the cathode and the anode, and losing electrons, gaining electrons. So we have talked a little bit about each of these. Okay, we have discussed precipitation reactions a lot already in 4.2. Remember, the net ionic equation for precipitation reaction happens when you have, based on solubilities, two aqueous reactants that form a solid. And if you need to refer back to your solubilities rules when you need to. Okay, so we're not going to take any time to focus on those anymore. Instead, we'll focus on the other two. A broad definition of acid and bases is that an acid is a proton donor and a base is a proton acceptor. When an acid and base react, the extra hydroxide and hydrogen ions do not like to remain ions, so they react to form water. So the net ionic equation for an acid-base reaction is called the neutralization reaction, where you will have the formation of water from the hydrogen ion and the hydroxide ion. So if you were ever to do a net ionic equation for a reaction and it forms water, and water is liquid, then that's your neutralization reaction. They're called neutralization reactions because just enough base is added to react exactly with how much acid we have. So we say that the acid has been neutralized. It produces an ionic salt that usually is dissolved in water and water. Okay, so when you're doing an acid-base reaction, you could just use the H plus OH minus makes H2O, where everything about the acid would go under the H plus and everything about the base would go with the OH minus. Okay, so I'm going to do that this time in this unit to just save some writing. So what volume of a 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of 0.35 molar sodium hydroxide? Okay, well, I said I'm going to just use the net ionic equation. So everything about the acid is going with the H plus, everything about the base is going with the OH minus. Okay, so I need to know the volume, liters, milliliters, of 0.100 molar HCl, and that's needed with 25.0 milliliters of a 0.35 molar sodium hydroxide solution. Okay, and this is a 1-to-1 ratio, so that's good to remember that when we are there's 1 mole of H plus for every 1 mole of OH minus. Okay, so what we're going to do first is we're going to switch to moles of base. So I'm just going to put OH for base, okay? And I'm going to do that by multiplying by the molarity, because that's equal to moles over liters. And it's a 1-to-1 ratio. So now I have moles of H plus, and I'm getting rid of the moles of the OH minus. Moles are equal to the moles. Okay, now we need liters or milliliters, whatever you would like to report your answer in. But to do that, we need to use the volume or the molarity of the acid. And I like to just do it dimensionally because it's easier than plugging it into the molarity equals moles over liters equation, because everybody oversimplifies what it actually should be. They don't solve it right. So you would flip it upside down, where you put the moles, the 0.1 moles of H plus in the denominator, and then the liters will go on top in the numerator, and then that way, when you solve, you get a volume. And the volume is 0.0875. liters of HCl, or the H+. Okay? If you are confused about replacing acids and bases with H+ and OH-, please talk to me in class. Okay? But we're going to do that again for this next example. So, in a certain experiment, 28 milliliters of a 0.25 molar nitric acid and the 53 milliliters of 0.32 molar potassium hydroxide are mixed together. What's the concentration of the H+ or OH- ions in excess after the reaction goes to completion? So, my hint to you right here, do you see the word excess? We want to know what's left over of our reactants. So that means that we are going to be doing a limiting reactant problem. Okay, because excess means that we're going to have one of our products or one of our reactants left over, and we want to know the excess reactant amount left when the reaction has been done, has neutralized itself. Okay, so applying this to our net ionic equation, my acid information, I have 28.0 milliliters of a 0.25 molar solution, and I have 53.0 milliliters, of 0.32 molar. Okay, so this is a limiting reactant problem. We need to know which one is done. Remember that it's moles equals moles. It's a titration kind of problem, right? So the moles of the H+ will equal the moles of the OH- when finished. So what we're going to do is we are going to solve. I'm going to just solve for the H+ first, because I always do the first one, the left one first. I'm going to solve for the other reactant, and then I'm going to solve for moles of OH and see if they match or if one is bigger than the other. Okay, so 0.028 liters, that's of H+ times 0.25 moles of H+ over 1 liter of H+, and it's a 1-to-1 ratio, so 1 mole of OH for every 1 mole of H+. Okay. So the moles of OH that I got here is 7.00 times 10 to the negative 3. Okay, and that's moles of OH. So now let's solve for moles of OH, just moles of OH, and not even do a mole ratio, and see how do those compare. So we have 0.053 liters of OH, and multiply that by the concentration of the OH, and that's where I'm going to stop. So because I need to compare moles to moles of the same kind. Okay, so stopping there, we get 1.70 times 10 to the negative 2. Okay, now the top part says that you need 7 times 10 to the negative third, so 0.007 moles of OH to react completely to use up all of the moles of the H+ in the reaction. What that means, and that's less than the moles that we have present from the OH. Okay, so what that means is the OH is going to be left over. The H+ is going to run out because we need to use less OH to use up all of the H+ than what we currently have in the vessel. Okay, so the limiting reactant is the H+, so that means the excess reactant is the OH-. So now the question is asking us, what's the concentration of the ions left over in excess after the reaction's done? So we need to know the OH left over now and the concentration of it. Okay, so now we need to take moles divided by liters. We're going to need to, so this is all excess hydroxide that we're solving for, and it's moles over liters. So we need to know what's left over, and the way to find out what's left over, we need to subtract the moles. So we had 1.7 times 10 to the negative 2 to start, and when I subtract I'm going to subtract how many moles were used. So this is what was available, and this is what was used to get what's left, okay, when we subtract those. And then we also need a total volume, just like when we got back into molarity before, in this year, we need total volume, and so we need total liters of both solutions added together. So we would take our 0.028 plus 0.053 liters. Okay, so simplifying, when I subtracted, now there might be some more decimals in your calculator and all that, but this is what I wrote down. 1 times 10 to the negative 2 moles of the OH over 0.081 liters. So when you divide that out, the concentration is 0.123 molar for the OH. So that means that the concentration of the hydroxide that's left over is 0.123 molar. Okay? So that's another way that you can use acid-base titrations, or acid-base neutralization reactions. The other type of reaction is the redox, or oxidation-reduction reaction. This involves oxidation, which remember, oxidation means that you lose electrons, and reduction is when you gain electrons. We're going to talk about this more later, but for now, how we can spot oxidation-reduction reactions, redox reactions, is by what are called oxidation states. Okay, so redox reactions happen all the time. It's a transfer of electrons. For example, if you combine solid sodium with chlorine gas, you make sodium chloride. So we're going to show in a second how we know that would be a redox reaction. But first we need to talk about oxidation states, or oxidation numbers. These provide a way to keep track of the electrons in redox reactions, especially involving covalent substances, because electrons are shared in atoms and covalent bonds. So oxidation states are obtained by arbitrarily assigning electrons to particular atoms. And what they are, they're imaginary charges. So you'll have positive and negative numbers that you assign for every single atom in a compound. Now the sum of the oxidation states equals 0 for a neutral compound, but if it is a charged ion, then it's equal to the charge. Okay, so normally they're not charged ions, but got to be careful there. Okay, so the oxidation state assigning rules are here in your notes. An atom in an element is 0 if it's just an element, or it's diatomic. So it could also be Hunkel fiber elements that are also considered 0. So if it's by itself, or it's a diatomic molecule with itself, then that would be a charge of 0, or an oxidation state of 0. Okay, a monatomic ion is same as its charge. So what I mean by that is, like, sodium's usually +1, lithium will be usually +1, chloride will be usually -1, fluorine will usually be -1, like that. So it also tells you that fluorine is usually -1, oxygen is usually -2, hydrogen is +1 in covalent compounds. Rare is the case when it won't be +1. Even, so it has the example of NH3, ammonia here, it would still be +1 even though it comes second in the compound. So just be careful there. So now let's look at how do you assign charges. Okay, you should always assign one of them in a compound, and then you might have to do some math to figure out the rest. Or if you know 2 of the 3, so like if it had H and O in there, you'd be able to solve it. So for A, we have CO2. Okay, from these two, I know that oxygen is going to have an oxidation state of -2 because that's its charge. It's always assigned that, always. Okay, so then we need to solve for carbon. And carbon is going to be, I'm just going to plug in X for carbon's oxidation state, because I don't know what it is yet. And it's the sum of all of the oxidation states equals 0. So I have 2 oxygens that have a -2 oxidation state, and that all equals 0. So simplifying, we have X minus 4 equals 0. Now, X is equal to 4, right? But remember, this is like a charge, so we need to make sure that it says +4. So the oxidation state of carbon would be +4 and oxygen would be -2. Okay. Usually when we have reactions, I like to just put them above or below the numbers, and that helps me out. Okay, B, we have SF6. Well, on our table, it said that fluorine will be labeled as a -1. Okay, so then sulfur, X for sulfur's value, plus we have 6 fluorines, each with a -1 oxidation state, and there is no charge, so that is equal to 0. So X will be +6. Okay, so sulfur has a +6 oxidation state and fluorine has a -1. Now our last one, we have a charge. It's nitrate, NO3 -1. Okay, so oxygen will still be assigned as -2. But nitrogen now, when we're solving it, we're still going to put X in for now, and it's +3 times -2. It's equal to the charge, so it's going to be equal to -1, not 0 this time. So X minus 6 equals -1, so X equals +5. So the nitrogen is a +5 and the oxygen is a -2. You should always have a balance of positive and negative with your oxidation states. If you come up with all negatives or all positives, you did something wrong. Okay? Sometimes when you're looking at oxidation states in reactions, it's very easy to spot. So, for example, I talked about this before, when you have solid sodium react with chlorine gas to make sodium chloride. It's a redox reaction because the oxidation state of sodium, it's by itself, so that has a 0. It's only when it's in a compound would you assign it a charge. Chlorine, same thing, it's a 0 because it is by itself. It's a diatomic molecule with itself, so that has oxidation state of 0, because which one's going to get the plus and which one's going to get the minus, we don't know. But in the compound, sodium is always +1 and chlorine is -1. So we know that this is a redox reaction because the sodium starts out at a 0 oxidation state and it goes to +1, and the chlorine starts out at 0 and goes to -1. Okay, so when you see a transfer or a change in oxidation state, then that is telling you there's a transfer of electrons, and so you would classify it as redox. Okay, sometimes it's not so obvious, like when you have oxygen in 2 different spots, or you, so let's think about oxidation states here. Okay, well, for CH4, H is +1, and I have 4 of them, and there's no charge, so then that means that carbon would have to be -4. Okay, oxygen, O2, diatomic, keep it 0. And then for CO2, oxygen's in a compound, so now we assign it -2, and there's 2 of them, so carbon will be +4. I think we did that one just in the other example. Okay, and then for water, H is always +1, there's 2 of them, so it makes sense that O is a -2. Okay, so in this reaction, the carbon starts out as a -4, and it turns into a +4. The H starts out as a +1, and it stays a +1. The oxygen starts out as 0, and it goes to be a -2. Okay, so the carbon and the oxygen are changing their oxidation states. Now, sometimes with redox reactions, if you have more than just 2 elements involved, you are going to have some that stay the same oxidation state. So those are not considered in the cathode or the anode in the oxidation or the reduction side. It's only the things that do change. Okay, so this does have a transfer of electrons, so this would characterize as redox, but it's just a little bit harder to spot, and that's why I was showing it to you. Okay, so example 12, we are going to look at this single replacement reaction of magnesium solid with zinc nitrate aqueous turns into zinc solid and dissolved magnesium nitrate. We want to identify if it's a precipitation, a neutralization, or a redox reaction, and we have to support our choice with evidence. Remember, explaining. More explaining than you think you need is better for you. Okay? So now let's go, before we go through the list of the answers, let's figure out the net ionic equation. Okay? So just looking back at this, trying to show you how you can do this a little bit faster. So you notice how the nitrate is NO3 on both sides. Well, remember, and it's also aqueous. So then that means that the nitrate is a spectator ion. So then what's left, we can't cross anything else left off because there's a solid versus aqueous and a solid versus aqueous, okay? So the net ionic equation for this reaction is going to be magnesium solid plus zinc, and zinc has a +2 charge, don't forget it, aqueous, turns into zinc solid plus magnesium ion, which has a +2 charge as well. Okay, so after looking at this reaction, this net ionic equation, I can go ahead and eliminate something right away of the three. And that is that it's not a neutralization reaction because the net ionic equation doesn't form water. It's not the formation of water. H plus OH minus makes H2O, so then it's not neutralization. We can eliminate that one. We can also eliminate precipitation reaction because we usually have double replacement with two aqueous reactants involved in there to form one solid product that's a compound, and that does not happen either. So, by process of elimination, it has to be a redox. But that is proven by the fact that the magnesium and the zinc have changing oxidation states because here I'll change it to a different color. The magnesium solid will be a 0. The zinc solid will be a 0. Okay? And then if you have a charged ion, it's the charge of the ion. So the oxidation state in the zinc +2 is +2, and the oxidation state of the Mg is also +2. So the magnesium starts out with an oxidation state of 0 and goes to +2, and the zinc starts out with an oxidation state of +2 and goes to 0. Okay, so there's a change in oxidation state from reactants to products for two different things. So that is evidence that this is a redox reaction. Okay, so sometimes I don't really know if there's any on the homework that you have to identify which type of reaction it is, but there will be some on your quiz and on the test, on the unit test, and on the AP exam. So you need to be able to support with evidence yourself.